All right, so today I also forgot to hit record on the Google Meet, so here we go. I'm going to go over the notes from 10.2, which was the calculus of parametric equations. But before we do that, I'm going to mention a couple of problems that we went over from the homework set from 10.1. So here we go. First thing, you can skip number 17 because number 17 has hyperbolic sine and cosine, and we're not going to talk about that in this class until after the AP test. Then we talked about number 12. So we were given x equals 1/2 cosine, y equals 2 sine from 0 to theta, or from the theta is between 0 and pi. And so to remove the parametric or the parameter theta from this equation, we want to use that sine squared plus cosine squared equals 1 idea. And so in order to get this to be a just regular cosine and this to be just plain sine, what you can do is 2x would be equal to cosine because that's x is equal to 1/2 cosine, and then 1/2 y would be equal to sine. And so when we plug those things in for sine and cosine, we end up with 1/2 y squared plus 2x squared equals 1, which if we simplify, we get this. This is a ellipse. And so from 0 to pi would be just this half of the ellipse, and it would be traveling in this direction. For number 18, that's the other one that we talked about, x equals tangent squared and y equals secant. The hint that I gave was that you're supposed to use this trig identity, secant squared equals 1 plus tangent squared. So then you end up with something like this, y squared equals 1 plus x, and then you still have to graph the parametric. Okay, so those were the homework clues and problems that we talked about. Then moving into today's stuff, the calculus of parametrics. So we're going to talk about how we take the derivative and the second derivative of a parametric equation, and then also how we do things like find the equation of a line that's tangent to a parametric and points of horizontal and vertical tangency. So with that, here we go. First of all, taking the first derivative. So dy dx for a parametric where x is some function of t and y is also a function of t, it would be dy dt over dx dt as long as dx dt is not equal to 0. So this one hopefully is pretty straightforward and fairly obvious that that's, or hopefully that one makes the most sense. The thing that doesn't quite make sense at first is the fact that the second derivative is not the second derivative of y with respect to t over the second derivative of x with respect to t. That is not the case because, so the second derivative, because it's the second derivative with respect to x of dy dx, right? Or so it's the one more derivative with respect to x of dy dx. So since this dy dx originally now is in terms of t, what we can do instead of saying ddx for this is ddt of dy dx over dx dt, because then if you, when you're dividing fractions, if you flip and multiply, the things that we would like to cancel out do, and also it has to do with the chain rule of taking derivatives with respect to x. Okay, so the general idea here is that each time you take a derivative, you have to divide by dx dt. So the third derivative, you would be dividing by another dx dt. The fourth derivative would be dividing by another dx dt after that. So each time you take a derivative, you divide by dx dt. Okay, so that's the general idea with taking derivatives with parametrics. Now, we're going to actually do an example with that. So our example, we're going to use x is 2 root t and y is 3t squared minus 2t. We're going to find the first and second derivative and then evaluate it at t equals 1 for each of those. And so I'm going to go ahead and rewrite x as 2t to the 1/2 because then it's easier to derive. So taking the first derivative, fairly simple. You're taking the derivative of y with respect to t over the derivative of x with respect to t. So we should get, for this one, 6t minus 2 for the derivative of y with respect to t over t to the negative 1/2, because that's the derivative of this, 2t to the 1/2 with respect to t. Then we want to simplify this. T to the negative 1/2 in the denominator is the same as t to the positive 1/2 in the numerator. So we get t to the 1/2 times 6t minus 2. Distribute that out, and we're left with this. Then evaluating it at t equals 1, we get 6 times 1 minus 2 times 1, which is 4. The second derivative, we're going to take the derivative of this over dx dt. So the derivative of our derivative with respect to t is 9t to the 1/2 minus t to the negative 1/2. And then dx dt is the same as it was up here, t to the negative 1/2. So then distributing this t to the 1/2 through, since we put this into the numerator as a positive, t to the 1/2, we get 9t minus 1, and then evaluating that at 1, 9 times 1 minus 1 is 8. Okay, so that's the basics of finding the first and second derivative and then evaluating it for a certain value of time, or t, which is something that we'll want to be able to do carrying it forward, because that's going to apply to things like finding our second example, finding the equation of a line tangent to the curve at a specific value for t. So this time, x is 4 cosine t and y is 3 sine t, and we want the equation of the line tangent to the curve at t equals 3 pi over 4. So to find the tangent line, we need two things. We need the slope and we need a point that it's going through. So to find the point that it's going through, first thing we have to do is plug t into our function for x and y. And that's what we do right here. Cosine of 3 pi over 4 is negative root 2 over 2. Sine of 3 pi over 4 is positive root 2 over 2. So we get, for our x and y values, when we simplify them out, we get negative 2 root 2 and 3 root 2 over 2. Then we need the slope. So we need to take the derivative of y with respect to t over the derivative of x with respect to t. We get 3 cosine of t over negative 4 sine t. And we're evaluating this at t equals 3 pi over 4. So we get negative 3 root 2 over 2 over negative 4 root 2 over 2, which simplifies to 3/4. So now we have a point and we have a slope, and we can just stick this into point slope form, which, remember, is y minus y1 equals m times x minus x1. So then we're just plugging these values in. Y minus 3 root 2 over 2 equals 3/4 times x plus 2 root 2. Okay, so there's our second example. Our third and final example is going to involve finding points of horizontal and vertical tangency. So with that, notice we're finding horizontal and vertical points of tangency for this. So whatever we find for values of time, or t, where they're tangent, we'll need to plug those values of t in to find the points where the horizontal and vertical tangency occur. So here we've got x equals t squared plus t, y equals t squared minus 3t plus 5. The first thing we need to do is take the derivative with respect, or we need to find dy dx, which means we need to take the derivative with respect to t of y and the derivative with respect to t of x. So we get 2t minus 3 when we derive this, and we get 2t plus 1 when we derive that. And then horizontal points of tangency will occur when the derivative is 0 over something that is not 0. Vertical tangencies will occur when the derivative is something that is not 0 over something that is 0. So that means for this one, we need to set the top equal to 0. For this one, we need to set the bottom equal to 0. So that's what we'll do right there. And then we'll go through and solve both of these for t. And we find that t is 3/2 for this one, and t is -1/2 for this one. So that tells me that we don't have any cases where it's 0 over 0. So we're good. We don't need to do anything with that, except for now plug both of these in to find our values of x and y that give us a point of horizontal or vertical tangency. So plugging in t equals 3 over 2 to x and to y, if we simplify both of these things, we should get 15/4 and 1/2 for our x and y values. This is our point where there is a horizontal tangent. Doing the same thing for t equals -1/2. That's what we plug in. And we should end up with -1/4, 27/4 for our point of vertical tangency. Okay. So that's everything we did in class today. So just to recap real quick, we found first and second derivatives of parametrics. We found equations of tangent lines to a parametric, and we found points of horizontal and vertical tangency for a parametric. All right. See you guys in class tomorrow.